Hello, everybody. This is Veysel. I'm a PhD candidate at the Leiden University, and I have an MS degree in Operations Research from Penn State University a decade ago. And at the same time, I'm working as a principal data scientist at Johnson Knowles, which is a AI consulting company in the United States, working mainly in healthcare domain. Today, I'm going to give you a brief introduction to neural networks and then share some examples with some use cases and then go one by one on some certain use cases. Okay, let's start. This is there's a AI hype everywhere, as you know, from medical domain to space industry, from autonomous drive to sport industry, everywhere actually. So it's everywhere, even on your cell phone, even on your browser. So every industry right now try to embrace somehow AI into their business flows. So that's why no matter which industry you are in, you will definitely have an intersection with the AI. So you would need to integrate this technology into your workflow, which you are already familiar very well. Okay, so let's start with explaining the basic confusion between these terms. AI versus machine learning versus deep learning. These terms usually used interchangeably, so people usually try to use AI to explain all, which is kind of true, but they are hiding behind the fancy term of AI actually to sell their products. So let's make it clear and explain what these concepts are all about. Okay, so AI is an umbrella term. It has been on the table like since 1940s during the World War II. And it's the right now it's still the umbrella term for all machine learning and deep learning applications because it includes more than what ML and DL offers actually. Then machine learning starts in 1980s actually. So it's basically the main idea behind machine learning is that it's building the software that can learn from data. So that instead of trying to hard code specifically, giving data and then the output, try to let the machines learn this interaction between the input and output. And then deep learning is just the subfield of machine learning, which is the subtype of ML using multi-layer neural networks. So we can say that deep learning is actually a machine learning, which is using multi-layer neural networks. Okay. So let's visualize this better. On the left-hand side, you see the neural network. Neural networks is basically one input nodes, one output nodes, and one layer between input and output. Okay, this is called hidden layer. If you have one hidden layer, we call it neural network. If you have more than one hidden layer, that is the deep term comes from, which is called deep learning. If you have more than one hidden layer between input and output layers, it's called deep learning. So the basic difference between machine learning and deep learnings can be explained at the bottom of the slides. So in machine learning, we give an input and then create some features, usually handcrafted features, or apply some other tools to extract these features so that the model can learn better. And then feed it into our machine learning algorithms like random forest, SVM, etc., and then try to find the input, try to map the input to the output. In deep learning, it's the beauty of the deep learning. Actually, the feature extraction process happens inside the networks unless we have a specific purpose. Like if you have some features that as a human you already know, and it would be hard for the machine or the deep learning algorithms to learn this, you can still create these features and then feed into your network. But usually during the image recognition problem, especially in computer vision, you don't need to create those features and then you expect the models learn these features and then try to map the input to the output. So that's the beauty of the deep learning. Okay, so why this popularity right now? This popularity mainly comes from the hype in the industry. Usually, startups are driving this. Actually, right now, many startups are blooming, and then they are getting investments by offering some AI solutions. And there are many VC venture capitalists trying to make money out of these ideas and then invest their money. And there's a flow of demand actually in job industry. So as I said in the beginning, no matter what you are doing, no matter which title you will have in your business or in your job, you would definitely need to learn these skills to apply your work. Okay, so there are 5 reasons actually that drive this hype at the moment. So we can call them like the 5 decades of research since 1940s. This is the first reason. I'm going to explain each one of them one by one in the following slides. Okay. So the second reasons is the cloud services and the hardware capabilities. And the third reasons is lots of data. The fourth reasons tools of and culture of collaborative and reproducible science, mainly PyTorch or TensorFlow, open source libraries that make the coding easier in deep learning. And the last one, and resources and efforts from the large corporations like OpenAI, Google Brain, etc. Okay, let's see what's going on after 5 decades of research in machine learning. Okay, so everything starts in 1940s with the idea of electronic brain. During the wartime, you know, the Alan Turing was they are trying to break the codes for Enigma, and then the idea was to build some electronic brain to handle this instead of human power, right? So the idea was very primitive. They were using like a big machines to solve these basic problems. Right now, it can be solved easily. So there was no available technology at that moment. So in 1957, the first building blocks of deep learning is invented. Actually, it's called perceptron. Okay, so Rosenblatt, you see the picture of that guy, builds the first perceptron based on the idea of some neurons, which I'm going to explain in the next slide. And then the golden age of AI started. So the idea was to let the models, let the networks learn from the data, from the inputs and the outputs. We call it the golden age of AI. But in 1960, 69, 1970, there's a book published, Perceptron, and it's claimed that the simple perceptron is not able to solve simple XOR problem, and then it's hard to train such a machine due to the limitation in the technology. So the dark age of AI started. We call it the AI winter. So you see these terms a lot on the news, on the blog posts. Actually, will AI winter will come or not? So it ended in 1986 with the invention of backpropagation and gradient descent. So right now there was a dark period in the history of AI, but in 1990s everything starts to bloom, and then right now we are able to train deep neural networks with the help of the computation power and the data that we feed. Okay, so the idea was the first idea in 1940s was having a threshold logic to convert the continuous inputs to the discrete outputs. Okay, everything starts with this idea. How can we build such a machine that take the continuous inputs like a signals and then create a discrete output like 1, 0, cat and dog, right? So another seminal idea about this invention is the Hebbian learning, which is summarized as cells that wire together. So which means that if we can connect the cells together and then somehow find a way to fire together, we can have a network that could learn, right, by communicating each other. It looks like brain, right? So Rosenblatt took this idea and then created the first perceptron in 1958. So it basically takes a weighted sum and returns 0 if the result is below threshold, 1 otherwise. It's like an activation function, the primitive activation function here, threshold. So in 1968, 69, there's a book published named Perceptron by Minsky. That book claimed that this single perceptron approach cannot be translated into multi-layered neural networks because it cannot represent non-linear problems. So, and if you want to apply this neuron architecture into non-linear problems, it's impossible to train at that time. So, and then it would take forever to train. So, the fundings are dried. Everyone started to say that we are not using AI anymore because it kind of got a negative annotation at that moment. So people were trying to run away from the term of AI in that during that AI winter. So after 5 decades of research in machine learning, AI winter is finally over in just before 1990s with the invention of backpropagation, gradient descent, and multi-layer perceptron. These two terms are everywhere right now. For the last 30 years, we are still using the backpropagation and gradient descent because it's the backbone of neural networks that are everywhere right now. So the idea is gradient descent constantly updates and moves the weights and bias towards the minimum of the cost function. So this is all about finding the minimal point of the optimization function, right? Since you guys are all learning right now optimization techniques from different fields and the algorithms, this is some sort of optimization is everywhere in neural network. Actually, the idea is to find the minimal point given billions of parameters. The second advantage is, like, the second reason of this AI hype is cloud services and hardware, we can say. With the invention of, like, everyone is trying to move their data from on-premise to cloud if there is no classified data, right? And the Amazon, Google, Microsoft, Azure, these are all the big cloud providers that are offering cheap solutions to store your data and then process your data on the fly. So this is the first reason. And the second reason is invention of GPU and TPU, because in deep learning, what we do is basically matrix multiplication. And the CPUs that are invented by doing some other process to make the computers work actually may not apply this kind of intensive matrix multiplication. That's why GPU and then TPU is invented, which were mainly used, for example, GPU were mainly used in the gaming industry for the graphic processing, right? Right now, it's making the life a lot easier to train the model when you use GPU instead of CPU. Okay. The third reason is the lots of data. With the social media and the data collection tools are everywhere, technologies everywhere in our life right now. So there are many resources that we can collect data. So these data can define us, right? Define people, how they shop, how they talk, what they want. So this is an era of big data. So big companies are using this data to make money out of it, right? So this is one of the reasons that right now the deep learning techniques are improved that much. Why? Because with the conventional machine learning algorithms, when you feed more data, as you can see in this chart, the performance may not improve a lot. There's a point that is like stagnated, so it doesn't learn more. But with the deep learning, by like building complex networks between input and output, when you feed more data, the performance improves a lot. So which means that it wasn't possible without deep learning to learn from that amount of data before. The fourth reason is the open source technologies that makes the life easier, that programming easier, because coding deep learning is hard actually. But with the help of TensorFlow, PyTorch, Keras, like these high-level architectures and the libraries, you don't need to build a softmax activation function from scratch or do the matrix multiplication from scratch. No, you can still do. We still teach people how to do this to let them see what's going on under the hood. But right now, you can just create one layer with one line in PyTorch or TensorFlow. These are the top two libraries that are being used in research and industry at the same time. Keras, for example, is the high-level API of the TensorFlow. PyTorch is coming from the Torch itself. Like the TensorFlow is already written in C++, etc. So right now there are easy wrappers that help people, even the beginners, build neural networks with a few lines of code. Okay. The last reason for this hype is the huge amount of resources and efforts from large companies. So, like a Facebook, Google, these companies have enough resources to do some R&D, right? And then invest nice amount of monies to develop new techniques, and then hire brilliant minds to develop new the algorithms to learn from data efficiently, or to learn from small data efficiently. Okay. And most of them, these are all free resources. For example, GPT-3 is released by OpenAI, and it's not free at the moment, of course, but it opens a huge opportunities, like and promising step towards artificial general intelligence. Okay, so when we say artificial intelligence, we are not just talking about machine learning or deep learning, as I mentioned before, because AI is an umbrella term that are covering more than what we know in machine learning. So it's expert systems is part of AI, or robotics is also part of AI. In right now, when we say machine learning and deep learning, there are subfields of these technologies, which are like text to speech, speech to text is one vertical. Another vertical is vision, right? Image recognition, like video understanding, machine vision. Another one is NLP. The one of the biggest vertical in machine learning right now is natural language processing, extracting knowledge from unstructured text data, which I'm already working intensively at the moment. And so let's see how we can build a simple neural network from scratch. Okay, so now I'm going to make an intro to neural networks, and then start with building a simple network, and then doing some convolutional neural networks, and then introduce you some famous architectures in deep learning. Okay, so why we use neuron analogy? Actually I mentioned this a little bit at the beginning. So we can say that everything starts with 1960s with the idea of building a smart, intelligent machines, and the perception was a lot looked like a brain, human brain. So let me make an analogy here. So people are usually making the analogy between brain neurons versus neuron and the deep learning in the neural networks. So human brain is made up of around 100 billion neurons. Okay, so it's just the nodes in your deep learning in your layers. So when you compare it with the famous GPT-3, GPT-3 has 175 billion parameters. When you have 100 billion neurons in your brain, which means that you have around 500 trillion synaptic connections. Okay, the like synaptic connections means that the connections between the neurons in your brain, which can we can make a similarity between the weights, like the parameters in the neural networks. Okay, so neurons in your brain receive electrical signals at the dendrites. Like the dendrites are these connections to the neuron itself, and then send them to the axon. Axon is the output of that neuron. So it's very similar to what we see here, right? And then each neuron receives input signals from its dendrites, and then produce an output signal given something happening inside the nucleus. So we can say that in the neural network, we have an input. So the inputs can be called as a synapse. Okay, inside the neuron, there is an activation function happen. At first, we some product the inputs with the weights, and then apply some threshold, which is called activation function, and then create some output. So that is the reason people are trying to make a similarity, to make an analogy between the human brain and then the neural networks. Okay, actually, this is how we learn in our daily life. When you want to learn something new, you start read again and again, and when you spend enough time on something that you didn't know before, the connections in your brain is rewired. that makes the learning easier for you. Okay, so even if you don't know anything at the beginning, the more you spend time, the more you train your brain, and then the connections get some connections more brighter than the other, so you learn that subject that you didn't have any idea before. So the I can also make an analogy between like a smart people versus dumb people. There's no dumb people, of course, but smart people can have better weights in their brain given someone who has no idea about the subject, right? So which means that anything can be learned. So let's get into the details of how neural network works. We have input layer and output layer. Every layer between input and output is called hidden layer. If you have one hidden layer, it's neural network. All the neural networks are like all the deep learning networks. Deep neural networks are neural networks. But if you have one layer, it's called just the neural networks. There could be multiple hidden layers right after the first hidden layer. So that's why we usually start implementing the first hidden layer and the second instead of trying to define input and output, right? So we always have the input and output in our network. The other on the right hand side, you see the connections between the neurons highlighted. So we call this weight, like the weights between first neuron of the first input layer of the first neuron, first node of the first hidden layer. So there's a connection. So each node is connected to each other in this network. This is called fully connected networks. Okay, so this is the first level of weights, this is the second level of weights, this is the third level of weights. So there are some notations here. That's why I'm using this image, by the way. So we have the weights connecting the first node to the first node in the first hidden layer. So the connection between first and the second node is called W12. Okay, so we are going to use this notation to make the matrix multiplication later on. So we at first start from input layers, right? We feed data, like the data would be a row of data in your data set, like height, weight, age, etc. One row of data, like column A, column B, column C, the first row. We feed one row, and then we randomly have some weights here. I'm going to do the calculations in the following slide, but this is the basic idea what's going on in one neuron. Okay, we feed the data, these 3 data points in the input layer, get the sum product at first, like the weights multiplied by the value itself, and then the sum product, and then apply some activation function, let's say sigmoid function, to add some threshold, and then create some output based on the activation function. So the first is sum product, the second is activation function. Okay, the basic building block of neural networks. So let's make the picture bigger right now. We have the inputs. I'm reiterating myself, I know, but I just want to make it clear for you. We have the weights that are connecting the inputs to the next layer, okay, like the first hidden layer. There's a weighted sum, sigmoid function applied, and then there are some other hidden weights here. So they are you end up with value here, right? When you get the sum product and the activation, you have one value here. It's called hidden input. There's another hidden input coming from this one. So you have as many hidden inputs as the number of the nodes in your layer. Okay, and then you have the random weights here at the first iteration that's going to be learned. They are parameters, and you apply that again, like the sum product, and then activation function, and then the outputs. So sum product, activation function, and so on. That's the basic backbone of neural networks. So let's solve one single problem for feed-forward neural networks. Assume that we are trying to find the output of given 2 input. Like the first input says that's 6, 5, and we already assume that we already know the output coming from this to 6, 5. Let's say 6 is the number of hours that you studied, 5 is the number of hours that you slept, and the output would be the grade that you got from your exam. Okay, so at first we start with the first row, feed into the network, make the calculations, and then each there's a hidden value which is going to be calculated here, like this value will be multiplied by this randomly produced weight, and then there's a sum product here, and then the sum product will be applied to activation. So this is a metric multiplication, as you can see. X1 and X2 is this. So we multiply this with these weights, right? So there's a matrix multiplication. We omit bias here because we usually add bias after multiplying the x with W1. So it's basically x1 multiplied by W11 plus bias, okay? And then do the sum product. So at the end, we have the hidden values, okay, here. And then we apply the activation function. So when we have the hidden values here, we apply. So this basically shows how we do the sum product. Okay, so we multiply x with the w and then the x2 with the others, and then do the sum product. So we have as many hidden values as the number of nodes in the hidden layers. Okay, so you don't need to memorize or know everything. Maybe you already know all this, but you rarely need to code this up from scratch, because you don't need to, but you need to know what's going on to be able to interpret better your results. So let's solve a simple example one. So I'm going to do the calculation manually right now. Okay, the first, let's say we have a problem to find out the test score, to predict the test score of a student who studied, whom we know the number of hours studied and the number of hours slept. So this student 2 hours studied 2 hours and then slept 9 hours and got 92. Another student studied 1 hour and slept 5 hours and got 86. Of course, there are more than this when you try to find out the predict the test score, but assume that this is the only values that we have, only data points that we have, that we can see if there's a pattern, there's a relationship between these values and then the output. This is the idea of machine learning, right? We have the inputs, we have the outputs, we try to find out if there's a pattern. In neural networks, even these numbers could be random, okay? With one single layer and the infinite number of nodes, you could model this behavior. You could create the function between input and output, because in machine learning and deep learning, we basically try to create the function that converts the input to the output, right? So there is a theorem called universal approximation theorem. It says that any input and output can be mapped. Any input can be mapped to the output. Any function can be represented with one hidden layer neural networks, as long as there are infinite number of nodes. So you can add many nodes here in this hidden layer, and then you can randomly sample and you can formulate this. Okay, this is called universal approximation theorem. Of course, it cannot predict in the real world time because we just randomly sample, but the chances are high that there's a relationship between input and output, right, for the number of hours studied and then the test score. Okay, so we will feed each row one by one, which is called iteration, okay, in deep learning. And then when we are done with all rows, assume that we have 4 rows here. So we are training our model with 3 rows. So we will have 3 iteration. When the 3 iteration is done, we will have 1 epo. This is called 1 epo. So every iteration we feed 1 row. Okay, 2, 9 is, we have 2 inputs right now because we have 2 columns, hours studied, hours slept. We have 2 columns, 2 features. So that's why we fit this into input as a 2 and 9. We randomly initialize our weights between the hidden layer and then the input layer. We say that, okay, we can have 3 nodes in the hidden layer, okay, and then connect each node to each other, which is fully connected, which we call it fully connected. Now, the first thing to do is multiply 2 and 9 with the weights and then do the sum product for each node, right? Okay, so we are going to do this for first row and then end up with some output, and then find the difference between the output and then the desired output, and then do the optimization. So at first, we take the 2 and 9. We have the weights like zero point 0.2, zero point 0.6. Zero point 0.2 and zero point 0.6 comes from the first node to the second. The zero point 0.6 and zero point 1 is connecting the first node to the second node in the second layer, right? So that's why we have 6 connections right now, 2 times 3, 6. We also have bias, but I am ignoring bias at the moment, but we usually add the bias and then we say that the number of parameters is 9, right? For this first 2 rows, okay? Like the first 2 layers, because we have 2 times 3 connections plus 3 bias, 1 bias, um, like the one bias for the hidden, the second bias for the second node, the third bias is for the third node. So we have 9 parameters between first and the second layer. Okay, so we do the matrix multiplication between 2, 9 versus 0.28, and then sum product, we end up with 7.6. Okay, 7.6. So we do the same for the other weights, and then we end up with 3.9. So these values are the hidden values in the hidden layer. Okay, 7.6, 3.9, 6.5 all come from these weights, matrix multiplication. Now we need to apply something to end up with the hidden outputs, which is called activation function. So I need to apply some activations to find out the hidden values. Okay, right now I just did the sum product. So activation function is you give, like, this is the first activation function. We have several activation functions in neural networks. The most famous one is sigmoid, relu, and softmax, which I'm going to cover a little bit in the next slides. So we basically take the inputs and then apply into this chart, let's say 7.6. Now we are going to find the sigmoid output for 7.6. So 7.6 in the x-axis corresponds to around 99.94. Okay, here, this point. So we just apply sigmoid and then end up with this value. We apply sigmoid to 3.9 and then end up this value. Okay, now we have the hidden output values. So we are done with the hidden layer. Now we are going to treat this treat this data as if the inputs to my input node, right? Right now, from now on, I'm going to use 9994 as an input to the next layer. So we have randomly initialized weights that are connecting this hidden layer to the output right now. So what I'm going to do is replicate the same process. I'm still in the first iteration, right? I'm not done with that first row. The first row just end up in the hidden layer. Now I'm going to end up in the output to complete one iteration. So I'm going to do the same here. This is the sum product. This value is multiplied by 0.4, 0.5, 0.9, right? Each value, and then summed. Now I have 1.79. Now I'm going to apply sigmoid again, and then I end up with 85. This sigmoid is activation is like normalizing your data. It's one advantage of that one, but it's more than that because it needs to be a function to that you can get the derivation so that you can find a way to minimize it. Okay, right now when I end up with 1.79 and the ground truth, sorry, I end up with 0.85 when I apply 1.79 to the sigmoid. Now my first prediction is 0.85, but my output is 92. So ground truth is 92. The model, just looking at the first row and one iteration, it didn't learn anything, of course. It just learned how to find the its way to the end. Now it will calculate the difference between 92 and 0.85 and then try to back propagate this error. Okay, so let's explain here. So it's just find the difference in the desired values and then try to back propagate into the network. This is another algebra lesson actually, so I'm not going to explain how backpropagation works, but it's basically try to update the weights to minimize this output. So this is an optimization problem. So instead of 2 to 3 parameters, you have millions of parameters to find the optimal value, like the knobs to tune. So that's why optimization function plays a huge role in deep learning. So if you have a non-convex problem, there would be more than multiple optimal points, right? So the network would stack in local minima, and then it would just say that okay, I'm done. But there's a huge risk that it couldn't find the global minima. That there are more optimal solutions that the algorithm find. That's why you are needed, right? Human mind needed to find the best uh, combination of the algorithms and the techniques for any network. So let's go back and then explain again. So right now we have the difference between the desired output and then the first prediction, and then back propagate the error through network and update all these randomly initialized weights. Because we start with the random weights, and then now we update it, and then the next time I send the second row, the model will update again. So whenever you feed data and then iterate again and again, you end up with better architecture, the better weights. It's like a connection in the brain will know its way from the beginning to the end, right? So there are multiple activation functions in neural networks that we use. The most famous ones are sigmoid, ReLU, and softmax, which I reserved one slide just for softmax. So ReLU, for example, it just says that if the sum product is less than zero, do not return anything. If it is more than zero, like greater than zero, just return whatever the sum product is. Okay, so these are all the functions that you can get the derivation, so that you can apply some backpropagation through chain rules in the matrix multiplication. Okay, right now we just apply sigmoid. Let's see softmax output, because we were just trying to predict right now. We were trying to predict the test score like a continuous value. It was a regression problem, right? So what if this would be a classification problem in which you have multiple outputs that you want to predict at the end? So let's say you have the colors that you want to predict, or you have image classes like cat and dogs that you want to classify your images in, right? So which means that you need to have some activation functions in the output layer that would enable you to like squeeze your output value between 1 and 0. When you sum up, you end up with 1. So that's why in the multi-classification problems we use softmax in the output layer. Okay, softmax is this is the softmax function. Okay, so you use it in the usually in the output layer, and then when your network starts to propagate, like start from feed forward, and then at the end it just skews these values. For example, this is the output values in the last hidden layer, let's say. So let's in the output layer, let's say. Now when I apply activation function, it is skews between 1 and 0, right? When you sum up this, you end up with 1.0. Okay, that's why it's important concept, like softmax is an important concept in deep neural network. But as you can see, it rewards the high values a lot and punishes the lower values very much. So that's why softmax may not be interpreted as a probability score, but people usually do this for the simplicity. For now, you can still use this as a probability of belonging to one class. So we can say that softmax is a probability distribution over k different possible outcomes. Okay, so when you look at the probabilities, you can say that this data point can belong to green class with 50%, like the blue class with 30%, purple class with 10%. It's like saying that this image looks like dog for 50%, looks like cat for 30%. Okay, that's why how we use softmax in the output layer. So, and then when we find the output and then compare the ground truth, we end up with some log error that we want to minimize. That's why we are using loss functions to minimize this error. Okay, so backpropagation is an abbreviation for forward propagation of the errors. So the error that we have at the end will be backpropagated through the network. And then we are going to use gradient descent which is calculating the gradient of the loss functions, like the derivation of the loss function with respect to all weights. So weights are, all these conditions are weights, a parameter that you need to tune to get the minimal optimization functions, right? Like you try to minimize your optimization function. So how can you find a uh, way to minimize, like find the optimal point that would minimize the optimization function? That's why the gradient descent is highly important in neural networks. So there are different loss functions that are being used in different conditions, okay, different settings. So if you have a regression problem that we just have, right? So you can use mean squared error at the end. We ended up with 0.85, but the ground truth was 92. Now I can, when I apply this for the first three rows, because I had three rows, right? So when I get the mean square error, right, the difference between the desired output and then the predicted value, and then sum, and then get the square. So that would be my loss function that I want to minimize right now, because I want to make it smaller as much as possible. If I have a classification, and if I have a binary outcome like 1 or 0, cat or dog, I can use sigmoid in the activation in the output, because the sigmoid will return 1 and 0, right? And if I have multiple classes, I use softmax. And if I have multiple class, but one data point can belong to multiple classes, right? One comment, like one social media post would be like positive and sarcastic, right? And negative or sarcastic. So it can belong to two class. Or one newspaper, the news on the newspaper can belong to multiple classes like politics and economics, right? So 50% politics, 30% economics, 20% sport in just one single paragraph, right? So which means that you have multi-label classification problem. When you have that one, you use sigmoid, but you change your loss function to binary cross entropy. You usually don't need to memorize this, but these are the basic concepts that everyone needs to know, because you can know this, make this interpretation that I just did without even looking at the slides right now, if you can grasp the idea what's going on, okay? And you end up with different values each time when you use different loss functions. So, and in PyTorch or TensorFlow, implementing this is as easy as writing just one single parameter, like optimization is equal to Adam. When you say that in Keras, you say that, okay, I want to use Adam as an activation, as an optimization function. Okay. So what we do is, since you guys are all working in optimization field at the moment, so the goal in machine learning or deep learning is to reduce the difference between the predicted output and the actual output. So we have a loss function. Now we try to minimize the output from that loss function. So to achieve this, we run multiple iterations with different weights. That weights are all updated at each iteration. And then this helps us to find the minimum cost. This is called gradient descent. Okay, we have the weights, we have the inputs, we have some predictions coming out of our algorithm, and then we have the cost, we have the actual output, we have the difference between the prediction and the actual, and then the cost function is the difference between them. So let's say this is a saddle, right? So we can have one. Let's say if we have one minimal, like a global point, so this could be a convex problem, so it's easy to find. It's not easy, of course, but when you find the minimal, you know that this is one minimal. But in deep learning, this is usually a non-convex problem in which you have multiple minimal points that you may not be sure about if it's global or not. So it's like this kind of chart, okay? So let's going back. So there are multiple optimization functions. It's called like stochastic gradient descent, like momentum, Nesterov, adaptive gradient descent, RMS probe, etc. There are multiple of them that you can use, but right now we usually use Adam or NADM, okay, as a default. And then if you are very well what you are doing, You can always play with these optimization functions as well. Okay, so let's build one single multi-layer network. Okay, so MLP. Let's call it multi-layer perceptron. We can call it. I'm not sure if you know, but we can create neural networks in sklearn as well. It's very, it's not very flexible compared to Keras, but you can still do this if you want. If you already know, if you want to build a fully connected networks. So we have the data points, let's say X and Y. X is the input and the Y is the target feature, right? So I have the train and tested, I split it, I scaled. Scaling is important in neural networks. The high level architectures already handle this, but you need to know that if you are doing this by yourself by hand, you need to scale your data at first, because this is matrix multiplication and there is a sum product that's applied to a threshold. So if your values are highly in different scales, like the age is between 10 and 50, but the height is between 150 to 200. So which means that when you do the calculations, that the scaling would affect that the sum product. And the model, of course, will learn eventually, but it will take much more time, because it will start to minimize larger errors at first, right? And then try to backpropagate that error, and it will take time. So we start with scaling. We use MLP regressor from a sklearn neural network module, okay, class. So we say that we are going to solve the same problem right now, that like the number of hours slept and studied versus the number of like the grades on the test. So if you want to build one layer, you say that I'm going to use 3 nodes in the first hidden layer. If you write one value here, which means that you just want one layer in your network, because in sklearn, when you fit this, you don't need to specify the input and output, because input is already known by the number of dimension in your data, and the output is already known because this is a regressor. It should be 1, right? So you want to say that I want to use sigmoid at the output, and actually everywhere I want to use sigmoid, it says. So, and then I want to iterate 1000 times. So it's like epoch numbers in the Keras. So you do this 1000 times till the model learns. So and then you just fit. This is this is everything that we need to do to build a neural networks in sklearn. If you want to do the deep neural networks, this is multi-layer. That's why we call it multi-layer. Okay, so we start with defining the number of the nodes in each layer. So we say that 3 nodes in the first hidden layer, 6 nodes in the second, and one, so on. Okay, so I just added 3 layers instead of 1. So you do the same, and then in multi-layer perceptron, more than 2 layers usually not needed. It will just be expensive operation. So right now, let me correct myself. This is not needed actually, because this is enough. Okay, so let's do the same with Keras. Okay, in Keras, it's the high-level API of TensorFlow, because the TensorFlow itself, with the advent of Keras, people forgot to learn how to code in TensorFlow actually. Actually, it makes the TensorFlow popular, because it's hard to code in pure TensorFlow, no matter what people say. But in Keras, you don't need to deal with every bit of details of TensorFlow, because it makes the life easier to build the models. So we say that, okay, I'm going to build a sequential neural network, which is another term of fully connected networks. Okay, so I'm going to stack the layers one by one. This means, so and then I say that I'm going to use a dense layer after the input layer with 3 nodes, and then the activation will be sigmoid at that node. As you know, in the sklearn, we were not able to define multiple activations for each layer, right? Maybe there is, but I'm not familiar. But in Keras, you can define different activation functions for each layer. So, and then here I say that end up with one node, which is my output. Okay, the last layer that I define here is my last, like the output layer. And I also say that this is the input shape. So the shape of my input features is my input shape right now. Use mean squared error as a loss function to optimize, and as an optimization function, use Adam, and then print something like mean absolute error to the screen so that I can monitor my training, and then train this with 100 epoch with validation split 5%. So every iteration take the 20, like you take a 5% validation split and then produce some metrics for the validation split as well. This is one layer neural networks, and we have 9 parameters. Okay, we have 9 parameters for this single network. Why? Because as we said, we have one input layer, one hidden layer, and one output layer, and which means that I have 6 connection in the between input and hidden layer, and then the bias terms it's 9. Okay, so let's do the same for deep neural networks. I want to say add one more layer after the first hidden layer with 6 nodes, and use ReLU as an activation. So I just added one layer here. When I add that layer, the number of the parameters are increased like more than twice, right? Because I added 6 nodes, which means that I'm going to connect the 6 nodes with the output of the first 3 nodes in the hidden layer. And then I end up with like a one dance layer as an output and then run again. So, and then I end up with 40 number of parameters as a number of parameters. So I'm done. Now we can talk about the fully connected networks, like the different type of the networks. Okay, so different type of the networks. The first one is fully connected networks, we call it, which means that every node is connected to others no matter what happens. This is called fully connected networks. There's a high number of parameters populated because of these fully connections. You usually hear these terms like feed forward, which means that from left to right, feed forward, fully connected, FC, everything connected to each other. Because in the modern architectures, you don't need to connect every node to each other in CNN or RNN, okay? So, which means that you can solve image recognition problems with fully connected networks. It could be an overkill, but you can still do. You have the nodes, you feed the pixels as an input, and then you end up with output as a class. Okay, 1, 2, 3. Okay, but there's a smart way to do this, which is accomplished by convolutional neural network. Instead of feeding the entire pixels, okay, like 256 times 265 times 3, right? If one defines one image, if you have 256 pixels in each dimension in your image. Instead of doing this, in convolutional neural networks, there are stacked layers and some other architectures like pooling, uh, stride, filter, these kind of components of the networks that makes life easier and easier for the network to extract the features. Because in the fully connected networks, you are not giving the model the similarities between this pixels around one small point, right? That's why it doesn't learn from the similarities between that pattern. It just treats them as a separate data point. But in CNN, with the idea of this disadvantage, CNN is developed. Okay, it's not a new actually. It's developed in 18th as well, but right now it's the technology made it possible. Like the computation power made it possible to train huge networks right now. So in CNN, I have another example for CNN in this slide, by the way. You just focus on one part of the image at each time, okay? And then you try to train the model to extract features as human eyes can extract, okay? And then you end up with the fully connected networks at the end because there are some convolution operations here, and then you flatten and end up with neural networks as well, fully connected neural networks, and then you feed it into the output and say that, okay, this is a car, this is a truck, etc. Okay, so every CNN end up with a classification layer, classification head. This is called the head layer. So let's get into the CNN. So how CNN works, as I said, it's a nice idea of extracting features from image data that would be impossible for fully connected networks at the beginning, right? Okay, so the basic components is convolution, and then the pooling, and then the ending up with the head layer, which is the fully connected network. So in any image recognition problem, we have a variety of images in the same data set, right? Like different shapes, different colors, different contours, different contrast, different resolutions, and different angles. So it's not simple as number of hours studied and slept versus test grade, right? So it can be anything. And for human being, for a toddler, it's easy to learn. Even with the tail of a cat, it can say this is cat. But uh, in machine, in deep learning, you need to feed the model with as many the sample as possible to let the model can learn from it. Because as a human, the intelligence in our brain, the connections in our brain, even for a 4 years old kid, comes from millions years of experience in the human brain, right? So that's why we cannot compare this with the human. But that's why neural networks needs to be fed by millions of images to get a better accuracy, which is close to human. So let's try to solve this problem with fully connected networks at first. In the fully connected networks, assume that I have a one image, and then it's 265 56 versus 256 as a, like a, let's say, square image. Okay, so which means that I have that many pixels. So I have 265, 200, sorry, 256, 256, 256 at each row times 256. And this is three color dimension, like channel, RGB channel, right? So for the color picture, so you have around 200K um, uh, nodes in your first layer, input layer, which doesn't make sense, but it's what it is, right? So if you want to solve this problem with that quality of images, with that dimension, you would need 200K nodes in your input layer. And if you have 1000 hidden units in your first, right, in the first hidden unit, which means that you would end up with that many, like more than 200 million, around 200 million weights, like a parameter that you would need. So just for just to store the weights of the first hidden layer, like this first hidden layer, just to store the weights, you would need 1.5 gigabyte memory. So this is very highly expensive because you are going to more than one layer. You are going to need more than one layer. Okay, so which means that which is computationally expensive and slow, because which means that there will be matrix multiplication at each iteration, and then the back propagation will also way expensive than that you can imagine. Okay, so that's why you can solve this in this way. It would be an overkill, and then the less accuracy. Even you manage to run this network, okay, and then train 1,000 times, the accuracy would still be way below than the expected accuracy that you want to have at the end. So let's do this and then train with a fully connected networks, right? So I say that, okay, I have 6 classes at the end, not just cat and dog. Let's say I have cat, dog, deer, etc., right? And then try to classify my images into 6 different classes. So, and I say that just use 128 nodes in the first hidden layer, okay? And then use 150 dimension as an input image and 3 channel. So when you train this, so I just trained this and I ended up with 20% accuracy. It's not learning at all, you see, because it's fluctuating. And then after the fifth epoch, I end up with 20% right now, which is way lower. It's like a random, right? So in the sixth class, without training anything, you can just randomly say something, and then you say you would have 70%, like 17% accuracy, right? Because 1 out of 6 would be true. So if you do this, it is less like it's way more expensive, because and then no assumption of spatial correlation between the pixels is taken into consideration, right? Because when you have a in the dark image, for when you have a right like a tail and the color is black, and then when you have the next pixel and then the next pixel, you would have some idea as a human, right? The more that you see, the more informative that you are. But if you fit this into neural network, every pixel is treated in the same way, which is infeasible to learn, actually, even as a human. So that's why there must be a smarter way, which is actually there is, which is called CNN, right? So let's do the same with convolutional neural networks. In convolutional neural networks, instead of trying to feed every pixel, right? These are all the rectangle, all the squares are the 1 pixel, let's say. Instead of feeding all at once, just focus on certain areas, like the tail of a cat, eye of a dog, right? And then feed it into the next one, that's CNN layer, and then apply some max pooling. Like max pooling means that like there are some average pooling, mean pooling, max pooling. So it's just try to extract one value from the combination of that patch. Okay, so it's like downsizing. So you end up with, after each convolution layer or some max pooling, you end up with different representation of an input image. So this is one convoluted image, this is another convoluted image, right? It's like the filtering that you apply on your cell phone, right? So these are all the features that the model learn. Some layers learn the curves, some layers learn the fluffy parts, some layers learn the bright parts, etc. Okay, so and that way the model learns at each step in a different feature. That's why in the transfer learning we usually uh, take a backbone network which is trained on millions of images, right? And then change the classifier layers to be able to take advantage of these learned features. Instead of learn from scratch, we use this because the things that we need is the weights between the neurons, right? So which means that if you have nice weights, nice connections between the neurons, you would have a like near perfect combination of the parameters that you can tune just a few images in the head layer. Okay, this is called transfer learning, but it's out of our lecture right now. So let me summarize it. Input layer, we take an input by preserving its spatial features. So we are not flattening it, right? Because instead of multiplying 256 by 256 by 3, this is called flattening, okay, when you multiply 3 dimensions. What we do is just treating this as a 3D image, and then use like 3D, like 2D convolutional neural networks, 1D convolutional layers, etc., to keep the spatial structure of the image. In the convolutional layer, we extract features through strips and the kernels and the filters. Okay, there are different techniques to do this. That is already learned by the model. So each one of them learns specific patterns. And then the max pooling layer downsamples the rectified feature maps. It's like an activation function. But we also have an activation functions for convolution layers, of course. We usually use ReLU and then the batch normalization for after each convolution layer. But inside the convolution layer, there is a like right after convolution layer, we apply max pooling to downsample. This prevents overfitting, okay? Because when the convolution network learns this one, we apply some downsampling to end up with this one. Otherwise, the model will learn a lot from this detail, right? Instead of this detail, I hope you follow my cursor right now. We let the model focus more on the downsampled version of the image. That's why we call it max pooling, because there are a lot of details here. If we feed model this detail, it would overfit. It would stuck in some some dimensions that wouldn't be representative in the real world, or it wouldn't generalize further, because this is all about generalization on unseen data. Okay, so but if you want to train the same model with convolutional neural networks, we can just say that, okay, at convolutional 2D, by keeping the structure, right? Like this is 32, I said, like this 32 is the one parameter. So I'm using this as a filter and the stride, etc. There are some parameters that you need to check out later on. Okay, you don't need to know right now, but I just want to show you how you can build. So we use 2D and then max pooling, and then another 2D convolution layer and another max pooling. Now we are done. You can do this enough. Okay, you can add more, but this is enough for cat and dog or 6-class image classification problem. And then you flatten, which means that you flatten the output of the convolution layers, and now you have a fully connected network here. You add one hidden layer again. Use ReLU, right? ReLU after each convolution, and then the output you need to use softmax. Why? Because this is a multi-classification problem, right? So I fit this into my network through convolution layers, and then end up with the 6 nodes in the output with a softmax activation. So I will have the outputs from each node. When you sum up, you will have 1.0, and the highest node will represent one class. Okay, so I trained this 5 EPO as I did with the fully connected one, and I ended up with 77%, which is amazing, right? Like the same EPO, same image, same data set, but less parameters to learn, right? Because you are not feeding a fully connected, like flattened input right now. It is faster. It is cheaper than like the LSTM or the other networks. Yeah, even with the fully connected networks, and it's more accurate, like a three times more accurate than the 20%, right? So with just the simple CNN networks, you end up with cat and dog image classification, or 6-class image classification problem. So as we calculate the number of the parameters in the fully connected networks, you can calculate the parameters in convolution networks as well. But you don't need to, because Keras or the PyTorch, when you write that summary, you end up with all these calculations. Okay, so you end up, you know that how many parameters that the model needs to learn. So this slide shows how you can calculate the number of parameters after each layer. Okay, so I'm not going to explain this slide, but it's a nice one that shows how you can calculate the number of parameters that you can interpret your summary when you compile your architecture. So let's talk about the popular neural network architectures. The first one we already covered, right? The first two, fully connected and the CNN. And the third one is recurrent neural networks. Recurrent means there is not just feed forward, there is also backward connections, like a cycling connections between the neurons, which is quite useful for the sequential task. Sequential means like the order of the features are important for the outcome, right? Like that's why we are using this in NLP a lot. Like, so this is one simple text, a simple text sentence. If you want to predict the next word, right? The previous word is important and the next word is important. If I don't want to, if I don't know this word, right? So if I want to predict this one, I need to know what's going on before and after. So that's why RNNs, GRU, LSTM, long short-term memory, these kind of networks are developed. So inside each cell, for example, I just added one snapshot from LSTM cell. You remember the single cell in the neural networks is just one threshold, right? It just does some product, right? But in LSTM, there is an forget gate, input gate, some threshold values, some window size, right? To let the model memorize, remember how long, like the features before and after. That's why it's very important concept in neural networks, especially in the NLP. Okay, so another architecture is autoencoder. Autoencoder is having a network representing, like doing really good on original image dataset. Let's say original image, and then you add some autoencoder part. Its job is to squeeze the image as much as possible and then output the same image. So there's a three layer actually, like encoder net, three networks, encoder networks, decoder networks, and in the middle there's a compressed image. So which means that this compressed part represents the image as much realistic as possible. So it's not the same dog, of course, but when you train this network with this input and then this output, you can get this representation of the input. So this is highly important concept for anomaly detection, because in anomaly detection problems, you basically try to teach the model what is normal for that model, right? So when you have some abnormality in the data, this encoder will find that, because it's not going to create the same. So it will say that, okay, there's something wrong with this input. So it's very important concept in anomaly detection. So there's another popular concept which some people even say that this is the most exciting invention or field in the last 10 years of machine learning, which is called generative adversarial networks, developed in 2014 by Ian Goodfellow. So, and it was basic idea at first, but right now there's a lot of different applications, like generating fake images, right? Or styling like transparent slides, styling from one image to another, like zebra versus horses, or one photo to another. So this is very popular, which can be used in the real world a lot, and for the of course for adversarial. This is called adversarial, which means that we are trying to train two different networks, okay, generator and discriminator. The idea is to train both network as much as, like, in a level that would let the both network produce images in the same quality. So generator will produce some image without seeing the original image, right? And then discriminator jobs is to detect if this is fake or real. We feed real one, and then we get some random outputs from generator, and then feed it into the discriminator network. It says 0 and 1, and then generator only knows, okay, I failed. Okay, I succeed. Okay, I failed. So, and each time when you train both network a lot, you end up with a balance. You end up with a sweet spot point that the generator can produce images as realistic as possible from the training data. Okay, so that's why it's very important, and then people can generate some fake news, fake pictures, and transfer. That's why it's very open to adversarial attacks as well. Okay, because you don't know what model focus more on while assigning that class. So the last one is pre-trained CNN architectures. I mentioned this a little bit, okay, because if you train a network, a large network, these are all CNN, for example, this is a huge state-of-the-art CNN architecture, let's say. When you train this on million images in image data sets, right? So you basically have a model that are already learned what is edges are, what blue is, what purple is, right? What a dog looks like, what a car looks like. So you can just take this, cut the head, and put another like 100 new images that you wanna classify right now. Let's say you wanna classify tomato plants from potato plants. Okay, you wanna say that, okay, this is apple, this is pear, this is orange. So you have a fruit classification problem. Let's say, so you can use this backbone and then just change the head. Okay, classify head, and then you would end up with state-of-the-art model with less images. In right now there are multiple state-of-the-art CNN architectures that are available as a pre-trained model that you can just plug and play, right? In Keras, in PyTorch, you just use any model. So it's just like some binary files. We call it like a checkpoints. Okay, so you got the checkpoints like ResNav 101 checkpoints you use, and then you add your new images in the classifier head. So right now, for example, this chart shows that the number of the parameters, like the size of the areas shows the bigger, like the size of the network, like VGG is very large. We have ResNet, which is deeper than VGG, but the idea of residual networks make it faster than VGG, and it's better in terms of accuracy, by the way. So we can say that ResNet 101 is better than VGG 16, and much faster. But it doesn't mean that VGG 16 is not gonna beat ResNet in some problems. Sometimes this is better. So you need to play with different ones. That's why we have that many images. Okay. So we are done. I hope you liked, and I made you more excited about this subject. If you have any question, you can definitely ask me, send an email, or connect me to social media, LinkedIn, or my university page. Okay. Thanks for inviting me to this lecture as a guest lecturer. I wish you a success. Okay. Thank you again.